Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hi there, Herman and Corn. So this podcast is really, we love tech. Let's be honest. Herman is outstanding. So are you, Corn. We are a happy techie family, and we never stop learning or asking questions. And if you have your own tech question you'd like Herman and Corn to answer, send us an email, or if you know me in that weird place called the real world, send me a WhatsApp with your question, and I'll run the pipeline. It's currently a private pipeline because who knows what would happen if anyone could just send Herman and Corn whatever they thought. I suspect we get some very interesting ones, but for now, we are the pipeline managers. But do send it to me, and I would absolutely love to send your question to Herman and Corn. Herman and Corn, today I'd like to talk about another topic related to the Iran-Israel war that we lived through last summer, because there's just so much to, I think, unpack from a technical standpoint. And I say that knowing that when we're talking about this concepts like, international ballistic missile warfare, who are we kidding? Most of the information is going to be, beyond the reaches of the public domain. What I think is interesting is not all of it. As I mentioned, when we were sheltering for many hours deep in a car park, which was one of the authorized bomb shelters in Jerusalem, and I was just really, really fascinated to learn about the physics of international ballistic missile warfare, the sheer size of the Iranian missiles, the speeds they travel at, the incredible and almost mind-boggling physics of trying to intercept these things in outer space. I thought it was all, I was morbidly fascinating is probably the right word, because of the severity of the danger that it poses. But one thing that I was wondering, and there was many things I was wondering about, how does this world all work, is how countries would go about detecting missile launches in the first place. Because, we saw on X during the conflict, there's a huge world of OSINT commentators, open source intelligence, commentating on the course of the war, some more informed than others, and some offering some more credible bodies, some of them openly staffed by former National Intelligence Agency personnel, offering some analysis and even looking at satellite imagery. And I saw some interesting theories about why Iran was launching its missile salvos at certain times based upon the detection capabilities and their attempts to thwart that. I think probably the detection that Israel provides for its civilians is probably public knowledge, but nevertheless, I'm going to refrain from giving specific information and just say that the specific amount of time that we got for rocket alerts and the specific alerting cadence that we got wasn't always consistent, and suggested that perhaps there was different degrees to which Israel was able to detect the launch, because that would, translate into how early they could warn civilians. And of course, that really begs the question, well, how do you actually detect a rocket launch somewhere 1,000 kilometers away? We're talking about the world of remote sensing here, and rocket launches have big, loud thermal signatures. So we're talking about thermal sensing as well. But of course, that's not the only thing with a thermal signature. A forest fire has a thermal signature. And if you look at a thermal heat map of the world, like the ones that NASA make publicly available, anyone can check it out, you see that there's actually there's much more happening in the atmosphere of the world than you would imagine at any given point in time. From thunderstorms through to active fires, the world is lit up with all these data points. So without attempting to, guess information that we really can't do in the side of in the open source world, what do we know about what has been disclosed, or what is likely believed to be the capabilities of Israel working in concert with allies for detecting things like ballistic missiles Is it essentially the case that the moment a adversarial missile is launched into the atmosphere somewhere in Iran, that is detected, and the whole I guess pipeline is maybe the right word of what has to happen next, which is also mind-boggling. There's a huge cascade of decisions and mathematics that have to be computed massively quickly, ranging from the likely trajectory to the choice of interceptor missile to the interception point to the risk of populations that might be at harm through that potential interception point. So that, and then of course that's not even to mention the alerting systems going out to civilians. So it's a huge orchestra that happens. It's a back end that probably would make most tech backends for non-military purposes look kind of primitive. Let's focus today just on the detecting aspect of this picture, remote sensing. How do countries know when other countries launch hostile things like ballistic missiles at them? And what are the technologies involved in this very high stakes form of sensing?
Hey everyone, welcome back to my weird prompts. I am Corn, and I am sitting here in our living room in Jerusalem with my brother,
Herman Poppleberry, at your service. It is a beautiful day outside, but today we are diving into a topic that is, quite literally, high stakes.
It really is. Our housemate Daniel sent us a voice note about this, and it is something we have actually lived through recently. He was asking about how countries detect missile launches from huge distances. When you are sitting in a bomb shelter and the sirens go off, you realize there is this massive invisible infrastructure working at light speed to keep you informed. We saw this firsthand during the intense missile and drone attacks over the last couple of years, particularly in 2024 and 2025, when regional defense systems were pushed close to their operational limits.
Exactly. It is one of those technologies that you hope you never have to think about. But once you start looking into the physics and the engineering behind it, it is absolutely mind-blowing. We are talking about sensing events that happen thousands of kilometers away, often within seconds of them occurring. Right now, we are actually in the middle of a massive architectural shift in how this is done.
Right, and Daniel specifically wanted to know about the remote sensing aspect. How do you distinguish a rocket motor from, say, a massive forest fire or a weird atmospheric reflection? It seems like a needle in a haystack problem, but the haystack is the entire planet.
That is a great way to put it. And remember, we touched on some of this back in episode 175 when we talked about modern missile warfare. But today we are really going to peel back the layers on the sensors themselves. The first thing to understand is that missile detection is not just one thing. It is a layered system of systems. You have got the space layer, the terrestrial radar layer, and the signal processing layer.
Let us start with the space layer, because that is usually the first line of defense. If a missile launches in a desert halfway around the world, how does a satellite 300 or 400 kilometers up know it is happening?
Well, it actually starts even higher than that. For decades, the backbone has been the Space-Based Infrared System, or SBIRS, which uses satellites in geostationary orbit, about 35,786 kilometers up. At that height, a satellite stays fixed over one point. But as we speak in early 2026, the Space Force is transitioning to something called Next-Gen OPIR, or Overhead Persistent Infrared. In fact, the first Next-Gen OPIR GEO satellite is scheduled for launch in the mid-2020s, with the current planning window targeting around 2026.
Wait, why the upgrade? Was SBIRS not good enough?
SBIRS was incredible, but the threats are changing. Modern missiles are being designed with faster-burning, dimmer engines that are harder to see against the Earth's background. Next, Gen OP IR uses much more sensitive focal plane arrays along with improved sensors and processing. These are essentially giant digital camera sensors, but instead of seeing visible light, they are tuned to specific infrared bands.
Okay, so it is a heat map. But a rocket engine is basically a giant blowtorch. I imagine that stands out quite a bit, right?
It does, but space is surprisingly noisy in the infrared spectrum. This is what engineers call the look-down problem. The Earth itself is warm. Clouds reflect sunlight, which is called sun glint. You have got lightning, volcanic activity, and yes, forest fires. To solve this, the sensors look at very specific parts of the spectrum. Most systems use multiple bands, like the 2.7 micron band, which is where water vapor emits energy, and the 4.3 micron band, which is the signature of carbon dioxide.
Why those specifically?
Because those are the primary combustion products of rocket fuel. When you burn tons of propellant, you create a massive cloud of hot CO2 and water vapor. By looking for those specific chemical fingerprints, the satellite can ignore a lot of the background noise from the sun or the warm ground.
That is fascinating. So it is not just looking for heat, it is looking for the chemical signature of a fire. But Daniel asked about distinguishing it from a forest fire. A forest fire is also burning carbon-based material, right?
It is, but the temperature and the intensity are orders of magnitude different. A forest fire might reach 1,000 degrees Celsius, but a rocket motor is pushing 3,000 degrees or more. More importantly, it is about the physics of the plume. Have you ever seen those little diamond shapes in the exhaust of a jet or a rocket?
Yeah, the shout diamonds or Mach discs.
Exactly! Those are caused by the pressure of the exhaust interacting with the atmosphere. Modern high-resolution sensors can actually resolve the spacing of those diamonds. That spacing tells the system the thrust of the engine and the altitude of the missile. A forest fire does not have shock diamonds. It does not have a velocity of 4 kilometers per second.
So it is the combination of the chemical fingerprint, the extreme temperature, and the movement. But what about the motion Daniel mentioned? A missile is moving incredibly fast.
That is the second-order effect. The algorithms are not just looking for a hotspot. They are looking for a hotspot with a specific acceleration profile. A ballistic missile has a very distinct curve. It starts slow and gets incredibly fast very quickly as it sheds weight. A forest fire is static. An airplane is moving, but its engines are nowhere near as hot as a ballistic missile. Even a lightning strike, which is very hot, only lasts for milliseconds, whereas a rocket burn lasts for minutes.
That makes sense. But I am curious about the atmospheric events Daniel mentioned. Like, could a particularly bright reflection of the sun off a high-altitude ice cloud trigger a false alarm?
It actually has happened in the history of these systems. There is a famous story from 1983 involving a Soviet officer named Stanislav Petrov. Their early warning system, called OCO, reported what appeared to be several incoming American missiles. It turned out the system had mistaken the sun reflecting off the top of high-altitude clouds for the thermal signatures of launches. Because the satellites were in a Molniya orbit, a highly elliptical path, the geometry of the sun, the clouds, and the sensor created a perfect storm of false data.
That is terrifying. I mean, we are talking about the potential for accidental nuclear war because of a cloud.
Right. And that is why modern systems are so much more sophisticated. Today, we use staring sensors versus scanning sensors. Older satellites had to scan the Earth line by line like an old television. Modern ones, like the ones in the new Proliferated Warfighter Space Architecture, or PWSA, have huge focal plane arrays that essentially stare at the entire hemisphere all at once. They can see changes in brightness in real time without having to wait for a sensor to sweep across the area again. This allows them to do much better temporal analysis. They can see the flicker of the engine, the staging process where one part of the rocket drops off and the next ignites. That kind of detail is almost impossible to...
You mentioned the PWSA. Is that different from the geostationary satellites we talked about?
It is a huge shift. Instead of just a few giant satellites 35,000 kilometers away, the Space Development Agency is deploying Tranche, one of the PWSA in low Earth orbit at roughly 1,000 kilometers up. By the mid-2020s, the goal is to have on the order of 100 plus of these smaller satellites in orbit as part of Tranche 1. Because they are closer, they can see much dimmer threats like hypersonic glide vehicles, which stay lower in the atmosphere and are harder for the high-altitude satellites to track.
So we have these eyes in the sky staring at the planet. But once the missile burns out its fuel, it is not a giant blowtorch anymore. It is just a cold piece of metal flying through space. How do we track it then?
That is where the radar layer comes in. Once the boost phase is over, the missile enters what we call the mid-course phase. It is coasting. At this point, infrared is less effective because the object is cooling down, although high-end sensors can still pick up the faint heat of the re-entry vehicle against the cold background of space. But primarily, we switch to ground-based or sea-based radar.
And these are not just your standard airport radars. I remember we talked about the BGP networking for JFK Airport back in episode 287, but these military radars are on a completely different scale.
Oh, absolutely. We are talking about phased array radars the size of apartment buildings. Things like the Ballistic Missile Early Warning System, or BMEWS, and the AN/TPY-2. These use thousands of small antenna elements to steer a radar beam electronically. They can track hundreds of objects simultaneously.
Wait, you said steer the beam electronically? They do not actually rotate like the ones you see on top of ships?
Most modern early warning radars are stationary. They look like giant slanted pyramids. By changing the phase of the signal sent to each individual antenna element, they can move the radar beam across the sky in microseconds. It is much faster and more reliable than a mechanical dish. Some of these radars, like the over-the-horizon systems, can even bounce signals off the ionosphere to see over the curvature of the Earth.
That is incredible. So they are essentially using the upper atmosphere as a mirror to look around the bend of the planet.
Exactly. It is called skywave propagation. By using high-frequency radio waves between 5 and 30 megahertz, they can detect launches from more than 6,000 kilometers away. But there is a trade-off. Over-the-horizon radar is less precise. It can tell you something is coming, but it might not give you the exact coordinates needed for an interceptor. That is why you need the combination. The satellite sees the flash, the over-the-horizon radar confirms the movement, and then the high-resolution X-band radars lock on to provide the precise tracking data.
I want to go back to the discrimination part. Daniel asked about how we distinguish missiles from other events. We talked about forest fires and clouds, but what about decoys? If a country launches a missile, couldn't they just throw out a bunch of shiny balloons or heaters to confuse the sensors?
That is a very sophisticated question, and it is the heart of the arms race in missile defense. It is called target discrimination. When a ballistic missile reaches the vacuum of space, it can release decoys. Because there is no air resistance, a heavy warhead and a light mylar balloon will travel at the exact same speed on the same trajectory. To a simple radar, they might look identical.
So how do you tell which one is the actual threat?
You look at the nuances. You look at how the objects wobble or tumble. A heavy warhead has a different moment of inertia than a hollow balloon. You use multispectral imaging to see how they reflect light and heat, and you wait until they start to hit the atmosphere again. This is called the terminal phase. Once they hit the air, the light decoys slow down rapidly due to drag, while the heavy warhead keeps its momentum. This is where the physics of atmospheric re-entry does the sorting for you.
But by then, you only have seconds to react.
Exactly. That is the high-stakes part. The goal of the entire detection pipeline is to give the decision makers as much time as possible. In the context of what we experienced here in Jerusalem, the system has to calculate the predicted impact point within seconds. It has to decide which neighborhoods need to be alerted and which do not.
That is something I always found fascinating. When the sirens go off here, it is not the whole city every time. It is very localized. That implies the math being done is incredibly precise.
It is. The system takes the radar data, calculates the ballistic arc, accounts for wind and atmospheric density, and draws an uncertainty ellipse on the map. If your house is in that ellipse, your phone starts screaming. It is a massive triumph of real-time computation. We are talking about solving complex differential equations in milliseconds. And as of 2026, much of this is transitioning to a new ground architecture called FORGE, which stands for Future Operationally Resilient Ground Evolution. It uses AI to process the massive data streams from all these different satellites and radars simultaneously as it takes over more work from legacy systems.
You mentioned earlier that the satellites use staring sensors now. Does that mean they're capturing video, or is it more like a continuous stream of data points?
It is more like a high-speed data stream. Each pixel on the sensor represents a specific area on the ground. The system is looking for a change in the radiant intensity of those pixels. If a pixel suddenly gets 1,000 times brighter and that brightness starts moving across adjacent pixels in a way that matches a rocket's profile, the system flags it. But because the data volume is so high, a lot of the processing happens on the satellite itself. It is called edge computing. The satellite only sends back the data for the pixels that are doing something interesting.
What about the newer stuff? I've been reading about hypersonic missiles. Does that change how we detect them? Because they do not follow a nice, predictable ballistic arc, right?
It changes everything, Corn. Hypersonics are the biggest challenge for detection systems right now. Standard ballistic missiles go very high into space and then come back down. They are easy to see because they are high up and follow a predictable path. Hypersonic glide vehicles stay much lower in the atmosphere, usually below 100 kilometers, and they can maneuver.
So they stay under the radar, literally.
Exactly. They fly in the gap between where traditional air defense radars look and where some space-based sensors are optimized. This has led to the development of a whole new layer of satellites called the Hypersonic and Ballistic Tracking Space Sensor, or HBTSS. These are being placed in low Earth orbit, much closer to the ground, so they can track these dimmer maneuvering threats with much higher sensitivity. The first HBTSS prototype satellites were launched in the mid-2020s for on-orbit testing, and they are in the process of being integrated into the broader missile warning architecture.
It feels like a constant game of cat and mouse. Every time we get better at sensing, the missiles get better at hiding.
It really is. And it is not just about the hardware. It is about the AI and machine learning that processes the data. With the sheer amount of data coming off these new staring sensors, a human could never look at it all. You need algorithms that can filter out the noise of a sun-glinting ocean or a massive lightning storm in the tropics without missing the one pixel that represents a launch. This is where new AI-enabled ground systems come in, which have been a growing focus of recent defense budgets for processing space, and ground-based sensor data.
Speaking of noise, I was thinking about the environmental impact of all this. Does the constant monitoring of the Earth's thermal signature give us any side benefits? Like, could these same satellites be used for something else?
That is actually a really cool second-order effect. While these satellites are classified military assets, the data they collect is sometimes shared for civil use. For example, during massive wildfire seasons, the infrared data from early warning satellites can help fire services detect new outbreaks in remote areas much faster than ground observers could. They can see the heat signature of a new fire starting in the middle of a national forest almost instantly.
That is a great example of a dual-use technology. It is designed for war, but ends up helping with disaster management.
Precisely. And they also use it for monitoring volcanic eruptions. A volcano's thermal signature is very distinct, and being able to track the heat buildup before an eruption can provide vital early warnings for aviation and local populations. We have seen this used effectively for eruptions in the Pacific over the last few years.
I want to circle back to Daniel's question about how it is possible to distinguish these events. We talked about the spectrum and the motion, but what about the chemistry? Does the exhaust of a rocket have a specific chemical signature that we can see from space?
It does. This is where it gets really nerdy. When a rocket burns fuel, it produces specific combustion products like carbon dioxide, water vapor, and sometimes aluminum oxide. These molecules emit and absorb light at very specific wavelengths. By using spectrometers, sensors can actually identify the chemical composition of the plume.
So you can tell not just that a rocket was launched, but potentially what kind of fuel it is using.
Yes, and if you know the fuel, you can often narrow down the type of missile. A solid-fueled missile, which can be launched almost instantly, has a different chemical signature than a liquid-fueled one, which takes longer to prepare. Solid fuels often contain metallic additives like aluminum to increase thrust, which show up as distinct features in the spectrum.
That is wild. It is like a chemical fingerprint being left in the sky.
Exactly. And the resolution of these sensors is getting to the point where they can see the Mach disks in the plume. As I mentioned, the spacing and shape of those diamonds can tell you about the engine's thrust and the altitude. It is an incredible amount of information derived from just a few pixels of light. It allows intelligence agencies to identify the specific model of a missile before it even reaches its peak altitude.
It really highlights how much work goes into the back end. Like Daniel said, most people just see the result, but the orchestra of decisions and mathematics happening behind the scenes is staggering. From the moment the first photon hits a sensor in orbit, to the moment the siren goes off in our neighborhood, it is a journey of data moving at the speed of light.
It really is. And for our listeners, If you are ever looking at those satellite maps of the world at night, just remember that there are eyes up there looking at a much more complex version of that map. They are not just seeing the lights of cities, they are seeing the thermal pulse of the entire planet. They are looking for the 1 in a billion event that could change history.
So, Herman, if you had to summarize the key takeaways for Daniel and everyone else listening, what are the big things to remember about how we detect these launches?
I would say there are 3 main things. First, it is all about the spectrum. We use infrared because it cuts through the noise and highlights the immense energy of a rocket motor, specifically looking for the CO2 and water vapor signatures. Second, it is about the motion. Algorithms filter out static heat sources like fires by looking for the specific acceleration and speed of a missile. And third, it is about the layers. No single sensor is perfect, so we use a combination of satellites in high and low orbits like the new PWSA, A-constellation massive ground radars, and sophisticated signal processing to build a reliable picture.
And I think the most important thing for me is that second-order effect we mentioned, how this high-stakes military tech can actually help us with things like climate monitoring and wildfire detection. It is a reminder that even the most specialized technology often has broader applications.
Absolutely. And you know, it is funny. We live in this era where we take for granted that we will get a notification on our phones if something is happening. But the chain of events required to make that notification happen involves everything from orbital mechanics to quantum physics in the sensors. It is a massive global scale machine that never sleeps.
It really does. And hey, if you are enjoying these deep dives into the tech that runs our world, we would really appreciate it if you could leave us a review on your podcast app or on Spotify. It genuinely helps other curious people find the show.
Yeah, it makes a big difference for us. We love seeing the feedback and hearing what topics you want us to tackle next. Maybe we can do a deep dive into the ground systems like FORGE next time.
Definitely. And remember, you can find all our past episodes, including the ones we mentioned today, about networking and missile tech at our website, myweirdprompts.com. There is a contact form there if you want to send us a question, or you can find us on Spotify.
We have got a lot more to explore. I think next time we might need to look into how these interceptors actually hit a target moving at 5 kilometers per second. That is a whole other level of crazy math. We could talk about the hit-to-kill technology and the Golden Dome initiative.
Oh, I am definitely down for that. The hit-to-kill technology is mind-blowing. But for now, I think we have given Daniel a pretty good overview of the sensing side.
I hope so. It is a fascinating field, even if it is born out of necessity.
Well, this has been My Weird Prompts. Thanks for joining us for episode 292.
Until next time, keep asking those weird questions.
Bye, everyone.
See ya.
You know, Herman, I was just thinking about the sheer volume of data we mentioned. If those sensors are staring at the whole Earth, the bandwidth required to send that back to a ground station must be insane.
Oh, it is. That is why a lot of the initial processing actually happens on the satellite itself. They use specialized chips like radiation-hardened FPGAs to do the first level of filtering. They do not send back a video of the whole Earth. They only send back the data for the pixels that are doing something interesting. It is the only way to keep the latency low enough to be useful.
That makes sense. It is edge computing, but in space. And with the new laser links between satellites in the PWSA, they can pass that data around the world without even needing a ground station in every country.
Exactly. It is a mesh network in orbit. If they tried to send everything via traditional radio, they would clog up their own communication links. It is all about efficiency and speed.
It is amazing how every problem in this field has a solution that leads to another interesting engineering challenge.
That is the beauty of it. It never ends. The more we see, the more we need to process.
All right, I think that is a wrap for real this time.
Sounds good. Let us go get some coffee.
Deal.
And maybe check if Daniel has any more prompts in the queue. He has been on a roll lately.
He really has. I think he spends his whole day just thinking of things that make us have to do hours of research.
And we love him for it.
We do. All right, thanks for listening, everyone. We will catch you in the next one.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox Turbo.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.